Us alive, awake, alert. There's one person there at the back that's maybe a little bit alive. I've been asked today to give you a brief introduction as to why you do mathematics. How many of you know what mathematics is all about? No one. Ladies and gentlemen, seeing that you don't know where the importance of mathematics comes in, you've got a problem, a major problem. How many of you plan on entering the arena of engineering? How many of you would like a job in engineering one day? Put up your hand. And put it up nice and high, very high. Okay, now put down your hands. Those of you who did not put up your hand, I suggest that you go to the registration office and cancel your registration for engineering. Okay. I'm here today to tell you where you will be applying your mathematics. Somewhere in your course so far, you've done differential equations, you've done integrals. Is that correct? Do you know where to apply those things? What is the concept of using an integral? It seems that they're going to start later with their test this morning because there's no feedback here. They're not alive. Okay, let's rephrase the question. How many of you have heard the concept of using an integral in mathematics? Okay, so they haven't done mathematics, no. Okay, my apologies, I didn't know that. So that brings me, actually that's a good idea. When you do mathematics, you will be exposed to a concept which is called an integral and a concept called a differential. I operate in the field of robotics, where we design, build, program machines that can do things humans can do. Simulate concepts, part of it. And one concept that we use is to program robots in a factory environment that can run on a floor, and there's a line on the floor and it needs to follow the line. Now, it seems like a simple concept. But how do we get a robot to follow a line? Now, on the ground, you can see there are red lines, there are blue lines. How do I get a robot to follow that line? Okay, imagine the following. You're in a room, and there's a table in the room. And somebody takes a blindfold, and they blindfold you, so you can see absolutely nothing. And then that person asks you to walk around the table. It might seem like a trivial concept. Some people would just think and imagine in their minds where the table is, and they would close their eyes. Well, the eyes is closed anyway. Okay, Francis is playing with the sound. Okay, so somebody would close, you blindfolded, and now you kind of remembering where the table is and you're trying to walk around the table. Another person might go and say, well, I've been blessed with some arms and some legs, so let me use those. Another person might go, take his hand, and feel where the table is. And he might walk around the table. Another person might be walking, bumping the table using his leg. So I walk and I bump, and as I'm bumping the table, I get an idea of where the table is, and I can walk around the table. Now that is exactly the concept that we use to apply to following a line. The robot is as blind as a mole. A robot can't see. So what we do is we take a light sensor and we put it onto the robot. And that light sensor gives us information about the environment. What kind of information? A light sensor detects intensities of light. In other words, if I work on a scale between 0 and 100, it means that 100 would be pure light, where 0 would be a dark room, pitch black. So that light sensor will detect an intensity of the environment. And that's what I can use to follow the line. Now here, I'm going to show you just a concept a simple concept of how we're going to use that line following strategy. Now, in the right-hand corner of that board, you can see that there's a flow diagram of a concept which we call a PID controller. Now, I'll explain a little bit later what is meant by PID. The different terms PID. There are three controllers built into one controller. And that's what we use to get the robot, not just to follow the line, but to be able to follow the line that you don't see, that it actually goes and hunts for the line. As you can see in the corner up there, there's 1, 2, 3 of them. And that is in a closed loop. Now, I'm going to use some terms which some of you have never heard before. And I'm not going to try and explain what they're all about. What I would like you to take from this is that mathematics has got a place in engineering. Definitely it's got a place in there. Otherwise, we won't be able to design systems and work with systems. But when you start working with integrals and differentials, the first thing that you're going to realize is that, whoa, this is too much for me. It's a lot of mathematics. There's a lot of theory that goes behind it. But if someone hasn't showed you where to apply it, you're never going to think of, where can I actually use this? So what we're going to do is the following. Let's get going here. Let's see if it works. PID stands for three terms: proportional, integral, and derivative. Proportional, the first one up there, is when we work with robots, we take the value of the black and the white. Now, if I say black and I say white, it's got nothing to do with politics. It's got to do something with, there's a black line on the ground, and the environment on the opposite side of the line is white. And our task is for the robot to follow the line. So we need to look at the value of the black. We need to look at the value of the white that is given us by the sensor. And that is what we're going to use. So first of all, the proportional side is where we're going to look at how far are the robot actually from the line. If it's far from the line, we want to get back to the line as quick as possible. If we're close to the line, then our adjustment doesn't need to be that big. So I'm quickly going to explain how the proportional side works. The integral side is where we would like to use the history of what has happened with the robot up to that point and apply that as part of the controller. Then the last part is the derivative on that side, is where we would like to predict what the error might be in the future and bring that into how we're going to control the robot as well. Are you still with me? Okay, so this could be one of your questions in the test afterwards. In other words, explain what is meant by a PID controller. So you need to understand it's proportional, it's integral, and it's derivative. The first one is we would like to make the adjustment according to the error. If it's a big error, we want to make a big adjustment. If it's a small error, we want to make a small adjustment. The integral side is we build up a memory that we can use as part of the control. And the last side, the derivative side, is where we would like to try and predict what the error is going to be. In other words, if I've been traveling on the line and the history says that I'm on the line and my error is small, I would like to use that to control my robot as well. Okay. When you look at the mathematical description of that controller that you see up there, it is a huge equation because it consists of three different parts. And it is not an easy mathematical expression. It is, as it says over here, it is fairly complex. Now, fairly is kind of an understatement. So take out the fairly. It is a complex, very complex one. However, in the control industry, people are scared away by that equation because they don't understand how it's been applied. So once you get to your control of machines in your S3 level, or if you do your BTEC, you're going to have two subjects. The one is control of machines, the other one is automatic control. Now, in those subjects, we go into depth how to build that controller. Prerequisite for those two subjects are Mathematics 3 for a number of reasons. First of all, you need to be able to understand those three concepts up there and being able to apply it. Then somewhere in your mathematics, you're going to get exposed or not exposed introduced to a concept of Laplace. Laplace is a gentleman that came up with a bright idea on how to take something from the time domain, we transfer it into, well, we call it the S domain or the Laplace domain, simply because in that domain it's easier to do the algebra. If you work in the time domain, the mathematics are very complex. So you will get exposed to those concepts as well. And here it says, if you understand the PID controller, and you understand your proportional, your integral, your derivative side, the application of that becomes fairly easy. So let's have a look at how it works. There's our little robot. And we would like it to do a basic task. If you look at that picture, there's the black line over there. That is my sensor, and I've got two motors, a motor A and a motor C, that I need to use or to control my robot. In other words, if I'm on the line, I'd like to turn off the line. If I'm off the line, I'd like to come back onto the line. Remember, I said that that robot is as blind as a mole. All it gets is information from the environment through the light sensor. Now, a lot of people think that to follow a line is that the sensor needs to be on the line all the time, and the moment it goes off the line, then I need to make the adjustment. However, there's a slight problem. If I'm off the line, how does a robot know that I'm on the right-hand side of the line, or am I on the left-hand side of the line? The robot doesn't know that. It doesn't know that. So that is our first problem. So when you're tracking a line using a robot, you're actually not following the line. You're using the edge of the line. And we use a grayscale, but let's get to that just now. There's my robot construction. There's the black line. There's the steering direction. So we're going to go in a forward direction on that side. There's my motors, and there's the light sensor. Now, how do we follow that? I've mentioned that it's a blind mouse. What do we need? I mentioned earlier on the values for black and white. So I measure the value for black. Now, black is a low intensity. You're going to find that if you use a light sensor, you're going to have a low value for intensity, whereas white is going to be a high value. Okay, 50 is not much higher than 40. However, I'm just using it as a purpose for the explanation. If you really go and take the robots, your white value might be around about 78, close to 80. Black could drop down to about 35. So that gives you quite a range that you can work with. Then, now how does that relate to the steering of the robot? Here's an example. This robot will follow the line. Now this robot does not have the controller built into it. This is simply, if I'm on the line, I turn off the line. If I'm off the line, I will go back to the line. So I'm going to show you this video clip to show you how the robot behaves. You will also get frustrated because this robot is not very fast. It goes slow around the track. It's got a track, so it goes around the track. So let's see if it works. Murphy's Law. Okay, for some reason, the video clip doesn't want to start. So let's carry on. What actually is happening here is that there's your light sensor values. There you can see it's black on that side, and there's white on that side. And what we do is we define it that I turn left if the value is between 40 and 45. Let's go backtrack. I've got 40 and I've got 50 on that side. And what we want to do is we would like to find a value that is the robot would know that if it's above that value, I'm on the line. If it's below that value, I'm off the line. So that the robot knows where it is. And it's a simple calculation. I take the value of white, take the value of black, I add the two together, and I divide it by 2. What does that give me? Yeah, it gives me 45, but what actually did I calculate? I calculated the average value between black and white. In control environment, we say it is the threshold. In other words, If the sensor measures a value that is above the threshold, I know that I'm on white. Have you got it? If it measures a value that is below the threshold, I know that I'm on black. And that is what we're going to use, and that's what this picture is all about. That's what that picture is all about. I turn left, which means that I am on black. Turning left means I turn off the line. That means I turn towards the line. Right. And this will result in a zigzag motion. In other words, the robot would go on the line, off the line, on the line, off the line. So it goes with a zigzag motion on the edge of the line. And that's what we would like to eliminate. You can go and you can vigorously look for the line and you can zigzag. However, in a factory environment, you don't want your robot to shake as it follows the line, because it might be carrying some valuables that doesn't like to be shaken. So in other words, we would like our robot to swerve along the line with a smooth motion. So we need to eliminate that part. So how are we going to do that? This is actually good for it says down there straight lines, but it's actually good for curves. So if we go around a curve, we want to look for the line vigorously. But if I go down a straight line, I'd like to kind of swerve down the line. Right. Those two are the wrong way around. Okay. But now we can start working with that strategy on how to follow a line. And here we change. So now we add another region. You can see that now in that middle region, the robot would be on the line. If it's off the line, I would have that part over there. And that part over there is on the line. This works a little bit better. Because if I'm on the line, the robot would go straight. If I'm off the line, it will turn towards the line. If I'm on the line, it will go a little bit off the line. But now, can we add more regions? Can we add more regions? Okay. Can we add more regions? Yes. Mathematics can do anything. It's as Napoleon said, is that you only see the objective. The obstacle must give way. Okay, let's carry on. When we start adding more regions, that's actually the beginning of start designing that PID controller. So we add more regions. So that's over there. If we turn, we've got more than 3 ranges that we can use. The first approach is we just turn left or right. The second approach that we had is we go straight. But now we need more kinds of turns, and this is where your mathematics starts coming in. Okay, we've done some basic mathematics up to this point. But here we go. That's the first one over there. That's the first, just going zigzag. The second one, we've added the range in the middle. So in other words, if I'm on the line, we're going to stay on the line. And then the last one is we've added a lot more into it. Now I can see that we've got a straight line. And that straight line has got an equation for it. So if we go through it, you can see over here is we turn very smoothly on that line. If we're close to the line, we make a small turn. If we're far from the line, we would like to make a big turn. In other words, that's my line over there. If I'm far off, I need to get back to the line quickly. But if I'm close to the line, I can just take my time and get back to the line. And that is the beginning of the proportional controller. And if we go into it, we can go with a straight line, which is y equals mx plus b. Some people have learned that it's not a b, but it's a c, mx plus c. It doesn't matter. It's just a mathematical equation. How many of you have seen this equation before? All of you should have seen it, because you've got mathematics in matric, is it not? Okay, those of you who can't remember that, you need to go and revise it. Okay, now here we got y is the distance on the x-axis, and that's, well, you all know that. The point at B is where y intercepts it. Okay, so let's have that. We shift the center of the line to the number 0. There's my threshold. I subtract 45, which is the threshold value, from each of the values that the light sensor measures. So that's my threshold. Now I get a value from the light sensor. I take that threshold and I subtract that from the light sensor value. And that gives me something. That something is is the error. And that error tells me how far am I from the line. And now I use that value that I get over there to control my motors. If that is a big value, I'm going to send a big value to the motors to say, get back to the line quickly. Okay. If it says 47, then my error is 2. If I'm on the line, my error would be 0, so I would go straight. Have you got it so far? How many of you are mechatronics students? Excellent. And the rest of you? Mechanical? Civil engineers? Okay, there's no mechanical engineers here today. Oh, there's a few over there. Okay, civil guys, I'm focusing more on the mechatronics and the mechanical side than it is on, but you're going to use integrals and derivatives in the design of beams as well. But that's another lecture, another day. Okay, right. If I'm on black, so if it says black minus the error, it gives me -5. If I'm on white, my error would be 5. So those are the extremes. Okay, so there we go. There's a -5 and a 1 on that side. There's a 5 and a 1 on this side. And it depends on how that error is going to be, how quickly I need to get back to the line. And there we go, and you can see that there is how I'm going to adjust my controller. So in other words, my turn is equals, there's an m, which is the value of the line, multiplied by the error. And here you can see the range goes from -1, which is hard to the left, to +1, which is hard to the right. How many of you are still following me? Good. Let's carry on. Right. Right, so there's the line slope. We said that it's a proportional constant that we're using. We multiply that with the error and convert it into turn. Now, turn is a value that I will send to my motors. There we go. There's a K constant that I use as well. I'm not going to explain that now, because that's okay. And there's my line equation. In other words, there's my turn value. I multiplied by a constant over there, multiplied by my error. And that constant is something that I can calculate that, or I can start by thumb suck it. So I guess a value, put it in there. And then I start changing. I increase that value or I decrease that value. However, there's a guy by the name of called Ziegler-Nichols that came up with a table of how I can adjust that value. So there's actually people that did a lot of research on this that assist you on how to find the right value for that one. Okay. Then that is the output to my controller that I get. And that is called the proportional controller. The range is between 5 and -5. And if it goes outside of that range, then the robot cannot tell how far you are going to be from the line. So when you design this controller, you need to make sure that your range is something that the robot will actually be able to do. And you can play around with that. Some people prefer that range to be small, because then your calculations are lesser. Or some people say, no, hang on, we would like to have a wide range. That's also that you can do. So it's dependent on the task that the robot is going to do. It says there, if all white looks the same, it means that you can't see the black line. Okay. If you're too far from the line, it's going to give you a constant, which means that you're outside of the range of the controller. If that happens, you could have a sequence within your program that says, if that does happen, follow the following strategy. Start looking for the line. In other words, the robot would turn to the left side or to the right side until it finds the line. Okay. And we can go on, and there's a whole lot of things that we can go. However, if it's a straight line, then the controller would be nice and smooth and it follows the line. If it's a curved line, something else will happen, and there's a lot of theory that goes in. I would like to get to the following. Right, integral. Now we would like to improve on our existing controller. So now we're looking for the line in a zigzag way, but we want to eliminate that zigzag. And what we're going to do here is we would like to include the integral side of it. Now again, the integral side is advanced maths that needs to be implemented. If you're going the textbook route, these equations are nice equations. Okay. What we want to do is it says here the integral is the running sum of the error. In other words, as I'm looking for the line, there's going to be error along the line, and I'm looking now for the line. And I built a memory. So I know what was the error before, and I can use that to adapt my controller. Okay, and this is how we're going to use it. I read the light sensor, I calculate the error, and then I add the error to the variable. But remember, we've already got a proportional side in the controller. All we do now is it becomes a proportional plus the integral. And this one is calculated in that way. And we say here that we multiply the integral by a proportional constant, ki, to get the correction. So on the proportional side, I multiply by a constant. On the integral side, I also multiply by a constant. And these constants can be calculated. Okay, I've got 5 minutes left. Right, so here we go. And we calculate, we build up a memory. Then on the other side is, and we can go and run here through that. The advantage is that it builds a memory. It takes a while before it kicks in, because if it starts on the line, then there's no memory. So the integral only kicks in a period after I've started the line. So you will see in all these controllers, if you follow a line, when the robot starts on the line, it looks for the line vigorously until it's got a memory of the error, and then all of a sudden it starts going smoothly. And it follows the line. Right. And we can go through that. Then here is, we can add the derivative. And we said, what does the derivative do? First one is the proportional side. We would like to calculate what the error is, and we would like to make the adjustment proportionally to the error. The integral side builds a memory. The derivative side tries to predict what the error is going to be. Okay. So there we go through, and it says here, it tries to predict the next error. And again, we can go through a whole lot of things. And that is actually how my controller now looks like. There you can see is the proportional side. Okay, that's the proportional side. That is the integral side, and that is the derivative side. So I use three things. I use a side where I look at how big the error is. And I adjust according to how big that error is. If it's a small error, small adjustment. Big error, big adjustment. On that side, I look at the memory. And this is where your integral comes in. And on that side is where I use the derivative. I predict what the next error is going to be. There I use a memory of the previous one. Okay. And then we can go through a whole lot of things with a lot of realities on how it works. And let's see if this video clip, if it works this time. Look how smooth that robot is following the line. You could hardly see that it actually goes that zigzag way looking for the line. Well, this one you can see that when it goes around the corners, it's actually nice and smooth that it goes around the corner. But when it negotiates a straight line, you can see that it swerves along the line. Can you see that it jumps the gap in the line? If your robot speed is high enough, it will actually jump the gap in the line. But if the robot speed is too slow, when it gets to the end of the line, it's actually going to start looking for the line, turning around, and then following the other side of the line. And that is a simple way where we use mathematics. We use the integral side, the derivative side, to build a controller that can control the robot. How many of you would like to program a robot that can do that? Okay, now the guys on that side are very keen on doing it. Okay, you guys on this side? Okay, there's at least one lady on that side. It is fun programming robots. In mechatronics is where we start using the mathematics and we apply it. Some of the mechanical guys, when you get to the design of a factory and you're building your PLCs and your controllers on that side, you might use this as well. But it's a lot of fun. It's actually the application. When you go through and you do your maths 1 and your maths 2 and your maths 3, the lecturer is probably not going to tell you where you're going to use it. but there are much applications for this. So go through the motions of trying to understand what exactly it does. The integral, the derivative side. And if you do understand what it does, then it becomes easier to apply and use it within your control environment. If you've got any more questions about these controllers, I'd be happy to come to my office and or come to my lab and I'll show you how the robots work. And I'll give you a 10-minute introduction and leave you for half an hour that you can program the robot. Ladies and gentlemen, thank you for your time and good luck with your test.